Hi everyone, I'm Giacomo Cignoni from University of Pisa, and today I'm presenting CLA, latent alignment for online continual self-supervised learning, which is work that I did in collaboration with Andrea Cosso, Alex Gomez Villa, Jos van der Wischer, and Antonio Carta. So I'm starting by having a quick recap of continual self-supervised learning. The objective is to train an encoder to extract a meaningful representation from a sequence of unlabeled data. As in a classical continual learning scenario, this sequence of data continually changes. And yeah, usually we focus on instance discrimination self-supervised methods, which from each samples extract 2 or more augmented views and then pass them through the encoder. And then those views are made are enforced to be similar by some kind of self-supervised loss, which can be like contrastive losses, like used like in SimClear or other kind of losses. So in continual self-supervised learning, how is forgetting usually prevented? The most popular approach is alignment. This approach consists in passing the current network features through an additional projector that projects the features in the past feature space. Then we take the features that are obtained from a frozen network at the last pass boundary, and then we enforce the projector features to be similar to the frozen network features. And this method is used by multiple papers like Castle, PFR, Pocon. And basically, at the end of the day, you have the final loss is something like this, that you have the self-supervised loss plus a regularization term that is composed by this alignment loss. Okay, so we start from like the conventional multitask, multi-epoch continual learning scenario, and we want to move to an online scenario where you have one pass stream, and and data comes in the form of very small mini batches of around maybe size 10, and yet more importantly, there are no task boundaries available. They are not explicit to the model. This comports that we have a limited computational budget that is caused by the one pass stream and the fact that we have very small mini batches, which contrasts with the main paradigms of self-supervised learning, which usually requires hundreds of epochs to converge and sometimes even very large mini batch sizes, especially for contrastive methods. So the first challenge to adapt continual self-supervised methods to an online scenario is overcoming the task boundaries absence. This means that we can't access to a frozen model at the last task boundaries. So we propose to use a copy of the model that is updated with an exponential moving average of the online model. So the weights updates very slower because it's an exponential moving average, and this exponential moving average network has a better representation of the past and can be used instead of the frozen network. So the second challenge is the small mini batch size of online continual learning, and it is usually overcome in the literature by the usage of a replay. So basically, we can concatenate the stream samples with replay samples to obtain a larger mini batch. And the combination of alignment with an exponential moving average network and replay is basically our first method, which is CLA-E. E stands for exponential moving average. And one particular thing that we did is that we kept in mind the stability plasticity trade-off. We wanted to maintain stability for past samples in the buffer. So we do only the alignment process for samples coming from the buffer, while the current samples coming from the stream are not subject to this alignment loss, and thus they are granted more plasticity in this way. The second method we proposed is CLA-R, which is similar, but instead of using the exponential moving average network as a target for the alignment loss, we instead use representations that were previously stored in the buffer as target for alignment. So yeah, the buffer looks something like this. With instead of having only samples stored in it, we have paired samples and past features, and those paired features are extracted and used as target for alignment. So the next question we pose ourselves is which kind of buffer is best to use in this scenario? So the de facto standard for especially for online continual learning is using a reservoir buffer. The reservoir buffer is very popular because at the end of the stream, it converges to an unbiased subset of the stream. So it is not biased towards more recent experience, and each sample has the same probability to end up in the buffer at the end of training. But the problem is that it is the fact that it represents only a subset of the entire stream. So while it is good at preventing forgetting, it's not very good for plasticity because at the end of the day, the samples that are inserted in the buffer, more the training goes on, less is the probability that those samples are replaced with newer ones. We compared it with a FIFO buffer, which is, let's say, number, because it can be seen just as a sliding window on the stream. And of course, it's not very good at preventing forgetting because it's a very shorter memory, but it can grant equal extraction for all stream samples. That's because the sample in the sample in the stream spend the same amount of time inside the window of the FIFO buffer. So basically, because forgetting and continual self-supervised learning is quite scarce, especially in an online scenario, and because the forgetting is already prevented by the alignment loss, we decided to use a FIFO buffer for CLA, and we empirically proved that it returns better results than using reservoir. We compared also with MinRed, which is another stability biased buffer. And yeah, so moving on to evaluation, a problem that we face is how we can compare different online continuous self-supervised learning strategies amongst them, and especially against an IID offline baseline. The fact is that, as we have seen, the limited computational budget is an important constraint and has to be considered. So we tried to approximate the computational budget using a novel metric, which is quite simple, actually. It is called cumulative backward passes, and it counts the number of backward passes that have been done in the entire training. So for short CBP, it is just calculated as the number of views extracted by the self-supervised models times the number of training steps during the whole training, times the B, which is the batch sizes, which is composed by both stream and the replay samples. And yeah, this metric is simple, but we prove that it is linearly related to the actual computation time. So we think that is a very good basis for comparing different models. So next, experiments. Yeah, we compared our methods, CLA-R and CLA-E, with other continual self-supervised methods that were applicable to the online setting. And also we compared to an IID baseline that was calculated with the same computational budget using a CBP. We used the class incremental CFAR 100 and Emergent 100, but with a fixed CBP budget. And we used the two metrics. One is final accuracy, which is the accuracy calculated at the end of training, at the end of the stream. And the other is average accuracy, which is the average of the accuracies each calculated at the end of each experience. So this metric is important because it can measure also the speed of convergence, because you get an idea how the model, how good is the model throughout the whole training stream. And of course, being in a self-supervised setting, we have no labels. So all the evaluations is done by linear probing. So yeah, as you can see from the results, CLA gets more or less state of the art for most cases. And next, I have a little bit of a summary of the most important findings. The fact that CLA is able to beat the IID baseline was quite surprising for us because we didn't expect this, because usually IID in continual learning is regarded as an upper bound. And this hints towards the possibility that self-supervised for self-supervised learning, IID training is not the most efficient paradigm, at least for a setting with a constrained computational budget like online. And another thing that we noted is that CLA has a better average accuracy compared to other methods. And this means that CLA is faster to converge and not only obtains a higher accuracy at the end of stream, which is a strong desiderata in online continual learning because you don't actually, in real world scenarios, you don't actually know the actual length of the stream. You don't know when it ends. So you want your model to be able to do evaluation anytime. So finally, we expanded a little bit on the fact that CLA can beat IID. And we wanted to prove that not only the CLA provides better representations, but that a CLA pre-trained model can be further trained, and thus it is the fact that can be a basis for further pre-training to obtain an even better model. So basically, we took a CLA checkpoint, and we continued its pre-training with a full with an IID training, with a multi-app training IID, and compared it with fully IID training. Yes, I can show maybe. Yeah, the green lines is the additional IID training to the CLA checkpoint, while the red dots are the full IID training, and on the x-axis you have the computational budget. So we can see that yeah, CLA plus IID can beat the full IID training, and this was also quite surprising because we didn't think that the representations that were obtained from CLA were also resilient to further training. Of course, if you take full CLA training, you can't reach full IID training for higher computational budgets. As you can see, the situation reverses when the computational budget gets higher. But that's, I think, is quite natural because CLA is optimized for like an online continuous scenario and not an unconstrained scenario. So that's basically. Thanks for your attention. You can find the code here. And yeah, if you have any questions.
Who's first then? Me? Okay, thank you for the talk. I want to ask like a more conceptual question because you're in an online setting. Can you comment on why you chose like such a heavy SimSci Baltoon, whatever, like dual pass model approach, or conversely, have you tried maybe preliminary using something like previous pretext tasks like jigsaw rotations or whatnot because they're computationally like faster? And like the SimSci approaches, they are known to notoriously require like many iterations before they really start kicking in.
Okay, actually, we didn't try other. We only tried like more heavier self-supervised methods like masked autoencoders, but we didn't go in the other way because at the end of the day, we didn't require compared to like online continual learning papers for supervised models. We kind of require the same amount of computational budget for obtaining our results because. The fact is that we use linear probing that is done offline as an evaluation method, and then that kind of helps the final accuracy of the model. Yeah, also the main focus of the paper was like concentrating on instance discrimination methods. I think also that probably the rotation methods are more outdated and not so competitive. So yes, maybe they are less computationally expensive because you only have to do one forward and backward pass, but that comes at the expense of also accuracy at the end of the day, I think.
Are you sure about that? Like, because recently there was a paper that did exactly that.
Okay. I didn't know that paper. Can you link me that?
Yeah. We can.
Yeah, we have a
discuss
chat.
later. Thanks for the answer.
So the last question.
Hello. So on your previous slide, when you were showing the plot when you add the editor, yeah. So I noticed that on image 900, the performance of the green box in the low compute, it's higher than when you have more compute for it. Like at the very end, you see the green box.
Yeah, that is a phenomenon that we are currently trying to explore. The fact that when you're trying to scale online continuous self-supervised methods to longer training, they do not always work very well. Because most of them are made to work in a scenario which requires quite a lot of prevention of forgetting, and this is at the expense of plasticity. So IID, on the other hand, is a fully model focused fully on plasticity. So when you have a higher computational budget, you don't have any problems in reaching higher accuracy. While here, in this case, if your model is too focused on stability, like for the CLA case especially, you can have worse performance because you don't learn enough from the novel data. And yeah, we are doing some more works in this direction and trying to explain and prevent this phenomenon.
Thank you.
Thank you.
Let's thank the speaker again.